Picture this, you are faced with an urgent need for cash and the clock is ticking. What's your game plan? In today's video, we are tackling a unique challenge that puts your financial instinct to the test. We'll break down the ins and out of borrowing money and how to navigate the tricky waters of interest and repayment. Curious to see how we can make the best financial decision? Alright, let's dive into this problem step by step and unpack the logic behind the solution. We are dealing with a graph-based scenario where we need to analyze connected components. So grab a cup of coffee and let's break it down. First off, the problem involves reading the input that describes a group of borrowers and their relationships. We start by capturing two crucial pieces of information, the number of borrowers, let's call it N, and the number of connections or M. These values set the stage for our graph structure. Now you'll notice we have an array called money. This stores how much each borrower has. It's essential to keep track of our goal. It's to determine the maximum amount of money we can borrow from any connected group of borrowers. Next, we set up an adjacency list called ADJ, which represents our graph. Each borrower has a list of other borrowers that they are directly connected to. This is where the relationships comes alive. For every connection we read from the input, we add it to our adjacency list, ensuring that the graph is bidirectional. So let's get to the goal, let's get to the heart of the logic with our visited array. This is a simple but powerful tool to keep track of which borrower we have already explored. As we traverse the graph, we want to avoid revisiting any borrower. Like each time we want to find an unvisited borrower, we know we have stumbled upon a new connected components. So what happens when we discover a new component? We launch into a depth first search or DFS, which is our way to exploring the graph. This is where we gather all the nodes in that component and store them in a list called component. Imagine it as collecting all your friends from a party who are interconnected. Everyone knows someone else in this group. Once we have a component, we pass it to a method called process component. This is where the magic happens. We start by checking the size of our component. If it's empty, we simply return a default value of 0 for the maximum sum and one for the count of ways to achieve that sum. An empty component means there is nothing to borrow from, right? Now, assuming we have some borrowers in our component, we create an index map. This helps us map borrower indices to their position in our component list. This mapping is crucial when we start building a bitmask representation of neighbors. Speaking of bitmask, let's dive into that. We set up an array called neighbor mask that will help us keep track of which borrowers are neighbors to each other in our component. This is like creating a secret handshake for each borrower, ensuring that we know who can be part of the borrowing circle without overlapping connections. Now here comes the exciting part. We use dynamic programming to explore all possible combinations of borrowers in the component. We iterate through each possible selection of borrowers represented by a bitmask. For each selection, we check if we can include a borrower without breaking the collection rule, meaning they can't be borrowed to someone already included in the selection. As we explore this combination, we calculate the total money we can collect and keep and track how many ways we can achieve that total. This is where the complexity of the problem really shines. As we balance maximizing our total with counting all possible combinations that yields the maximum, and that finally after exploring all combinations, we find the maximum sum we can borrow and the number of ways we can achieve that sum. This information is crucial as it answers our main question, how many borrowers we have collected and in how many distinct ways we can do it. In summary, this approach combines graph theory with dynamic programming, allowing us to efficiently explore possibilities and gather insights into our connected borrowers. The power of using DFS to identify components alongside dynamic programming to maximize our potential is a beautiful blend of algorithms and work. Alright folks, let's wrap up our deep dive into the borrowing money problem from HackerRank. We explored how we tackle this challenge by implementing a C-sharp solution that efficiently calculates the maximum amount of money that can be borrowed and the number of ways to achieve that amount. We use depth first search to traverse the graph of borrowers and develop a dynamic programming approach to compute the optimal borrowing strategies within connected components. Remember, the key takeaway here is understanding how to represent the problem using graphs and how to apply DFS and bit masking to solve it efficiently. If you have enjoyed this problem solving journey and want to see more coding challenges problem, make sure to check out the link in the source code below and hit that like button to subscribe to the channel. Your support really helps us keep bringing more exciting content, and stay tuned for more videos next time as we'll dive deeper into graph algorithms and real world application. You won't want to miss it. Keep coding and I'll see you in the next